Galvanic/voltaic cells, depending on whether you want to give Luigi credit or Alessandro credit. You can call them either one. So these cells are going to be taking a redox reaction and separating them physically so that the electrons lost, they're going to be gained by the other half reaction, but they're going to have to move through a wire, and we can put a circuit in there, in order to get some of the work done. But these, again, are spontaneous redox reactions. We'll have two half reactions, one oxidation, one reduction. The oxidation reaction will be losing electrons, the reduction reaction will be gaining electrons. All we're doing is we're separating them out physically from each other and getting the electrons to run through a circuit for us. So each of these cells, we're going to have an electrode and an electrolyte, and the reaction is going to take place somewhere in there, though there are also electrodes that are not involved in the reaction called inert electrodes, in which case it is all the electrolyte that is carrying out the reaction. The half cells are going to have to be connected with a wire to allow the electrons to transfer from the oxidation that is losing them over to the other half cell where the reduction is taking place. And there's also going to have to be a porous barrier, or often a U-tube is used to connect these guys together, because not only are the electrons moving between them, but there has to be a transfer of ions between the two cells as well. To do this, the U-tube, if it's being used, or if it's just a barrier, the ions can go right through the barrier. But if the U-tube is being used, it has to have its own electrolyte in it with its own ions, and we want them to be inert. So something like sodium nitrate is great because you're not going to have any side reactions happening with those ions. They're very soluble. They will stay in solution. And essentially what's happening with this is that the anions are moving towards, but importantly not to, the anode side, the half reaction that contains the anode. They're not going to move to the anode because, again, they are anions with a negative charge, and we're going to see the anode itself is negative. So they're not moving right to the anode side, they're just moving into the electrolyte that contains the anode. And then the cations with their positive charge, they're going to be moving towards the electrolyte that contains the cathode. And this is called internal transfer, and what it does is it maintains the neutrality of the solution, the electrolytes, in both of the half reactions. So essentially we're just taking a redox reaction and we're physically separating it out into two different containers where we have the oxidation happening in one and the reduction happening in the other. We're going to connect the electrodes. This is how the electrons are moving between the half reactions. Is they're going to go through a wire. We can measure their movement, or the potential difference anyways, with a voltmeter, the cell potential. We'll talk about that later. And there's going to be ions transferring as well. And so this salt bridge allows ions to move between the two half cells. And this is going to make sure that the solution that contains the electrodes is going to be remaining neutral. So we're going to be looking at ions moving and reactions happening, and the solutions are going to maintain their neutrality. The electrons are going to be moving through the wire, and we'll be able to figure out how much we can actually get in terms of voltage based on who it is that is going through reactions. So once the electrons are connected to the wire, the reactions are going to allow, assuming the salt bridge is also in place, the reactions, the oxidation, the reduction reactions will be allowed to start. And at the anode, this is where our oxidation occurs. So at the anode is where oxidation occurs. And oxidation is the loss of electrons. So what we're going to end up is there's going to be sort of a surplus of electrons building up on the anode here. And so it is going to have a negative charge. So the electrons are going to be lost from this half reaction, and they're going to be moving to the other half reaction where the cathode is. And the cathode is essentially consuming electrons, so it's taking in those electrons. So it's going to have a positive charge, and you remember that because there's a T in cathode. And again, a reduction reaction is taking place here, so the reduction is the gain of electrons. This is why the cathode has a positive charge. And they are getting their electrons from the anodes. The electrons are moving from the anode to the cathode, and those are our two half reactions. Same as a redox reaction we would have had before, but we just happen to have this one sitting in one beaker and this one sitting in a different beaker so that we can run our electrons through something like a circuit. So electrons flow from the anode to the cathode. Whichever half cell's reaction is higher on the redox table, this will be the strong oxidizing agent we're looking for. This is the one that is going to go through reduction, and that is going to be the cathodes. Remember, the oxidizing agent goes through reduction. Reduction is gain of electrons, and that will be the cathode that is doing that. The lower one, if we're looking at a redox table, whatever species we have to the lower right, that's going to be our strongest reducing agent, and reducing agents get oxidized, and oxidation happens at the anode. So, and again, as these reactions happen, the electrons are being lost at the anode where the oxidation is happening, and they are being consumed at the cathode where the reduction is happening. That's where our electron transfer is going. A couple of ways we can represent this. The quickest way is shorthand cell notation, and essentially as a standard we put the anode on the left hand side. So we take whatever the anode's made out of and we would write it on the left hand side. We then put a little line saying, okay, there's a barrier between the anode and it's sitting inside this electrolyte, but the anode is a solid. The electrolyte's going to contain some ions. We put two lines to separate out the two half reactions. So we just divide the two half reactions with those two lines, and we say, okay, there's some other electrolyte sitting in the other half reaction, and that contains the cathode. And the convention is to put the anode on the left and the cathode on the right. And so it doesn't have to be labeled anode. You know, if it's sitting on the left, like let's say this was, I don't know, iron or something like that. If it's on the left-hand side, then you know that it is going to be the anode. If it is on the right-hand side, you know it's going to be the cathode. So for example, if we had an anode of copper sitting in a solution that had copper ions, we'd write it like that. And then the other half reaction would have its cathode electrode as silver is sitting in a solution of silver ions, and then we would have this as our cell written in shorthand cell notation. So the single line is the phase boundary. So for example, the solid copper sitting in the aqueous copper ion solution. The double line is a physical boundary, so we would have one beaker over here, and then we have another beaker over here, and those two reactions are physically separated from each other. All right, so let's try drawing that one that we were just looking at. If we had some solid copper, some copper nitrate, which will give us our copper ions, our silver nitrate, which will give us some silver ions, and our silver metal. First thing we want to know is, okay, based on all of the stuff we have here, who is going to be the strongest oxidizing agent? And whoever it is the strongest oxidizing agent, that's the one that's going to go through reduction, and reduction is gain of electrons, so it'll be gaining electrons. We know reduction happens at the cathode, so this is going to be our cathode. And then we want to say, okay, of the things that we have here, what's our strongest reducing agent? Our reducing agent goes through oxidation. Oxidation is loss of electrons, and that happens at the anode. So we pull out our redox table, whichever one you have available to you, and we find out who on this table is involved in this reaction. And again, our strongest oxidizing agent is going to be up at the top left. So we start at the top and we work our way down. And we say, okay, who do we have here that's our strongest oxidizing agent? And our strongest reducing agent, we start at the bottom, we work our way up and say, okay, who's the strongest reducing agent? And we should be able to find, there's our silver as our strongest, the one that we have here. And this is a silver ion. So that is the strongest oxidizing agent we have. So that's the one that's going to go through reduction. That's the one that's going to be gaining electrons, and reduction happens at the cathode. And then we look for our strongest reducing agent, and we find that solid copper is the strongest reducing agent we have present here. And again, as long as our reducing agent is below to the right and our oxidizing agent is above to the left, we will have a spontaneous reaction, which is important. If you want a galvanic cell, it's got to be a spontaneous reaction. So it is going to be our copper that is going through a oxidation, and it is going to be our silver ions that are going through a reduction. So we can write those reactions out, and we can say, okay, it's going to be the copper that's going to start out as a solid, and it's going to be losing its electrons to the silver ions, which will then become solid silver atoms over here. So the copper is essentially going to give its electrons to the silver. The silver becomes solid silver, and the copper, which has lost its electrons, is now a copper ion. So that's the two half reactions that we're going to be carrying out. And when we go to set it up, we want to make sure that we know who's going through oxidation, who's going through reduction. And remember, oxidation is happening at the anode, and that's the strongest reducing agent that's going to be doing that. So let's write the two half reactions out so we can have a look at this. The silver is picking up. So here's the silver here. It's going to be picking up electrons. That is our reduction because it is the strong oxidizing agent. Our copper here is going to be losing its electrons, which is Oxidation is loss of electrons. That is our strong reducing agent. And remember, oxidation happens at the anode and our reduction happens at the cathode. So when we go to draw the actual galvanic cell, I would stick with drawing your anode on the left because that's what we have to do for cell notation. You don't have to do it for galvanic cells, but you might as well stick to the same pattern. So we'll put our anode with the copper cover on the left-hand side, the left beaker, and that'll be our anode. And then we will put our silver on the right, just because that's what we have to do for cell notation anyways. We might as well do it for when we're drawing our galvanic cells as well. And that way, every time we draw a galvanic cell, we end up with the cathode on the right and on the left, which is consistent. So start off with some sort of beaker with an electrode in it. We need to make sure that we have a wire connecting the two electrodes because otherwise the electrons can't flow. We have to have some way to allow ions to flow from one beaker over here to another beaker over here. So if you have a salt bridge and then that could be filled with a salt solution in here, that's why it's called a salt bridge. The other option is that you could have a special container that had a porous barrier where the ions could actually move right between the walls of the container, but just a paper towel between two beakers works pretty well too. All right, so then we start putting things in. We say, okay, if we want to stick to our anode and I want to put that on the left-hand side, then I know that this is going to have a negative charge to it. It is the one that is producing those electrons. The electrons are being lost here and they're sort of piling up on that anode. And this is copper that is going to be going through this. It's the oxidation, the loss of electrons. So this piece of copper over here that we're drawing, this copper anode is going to be losing electrons. And when you lose electrons, when a metal loses electrons, it becomes an ion. So essentially this anode is going to start getting smaller and smaller. It's going to lose its atoms because they're going to become ions. So the copper is going to be going into solution here because it's lost its electrons. The electrons are going to go, they're going to be picked up by the anode and they're going to be traveling all the way over to the cathode. And so the electrons are moving in that direction towards the cathode. The cathode has a positive charge, it's the silver, because this is where the electrons are being gained. And so we have to have something that would actually be picking up those electrons, and that's what these ions in solution would be doing, is that this silver ion, it wants to meet the electron that the copper gave up. It wants to take that and it wants to form an atom, and it'll actually get stuck on the cathode here. And so this cathode will actually start to get bigger as the silver ions pick up electrons and they start piling up onto the electrode. And so we want to show the electron transfer. We want to show the ions going through their reactions. So we have the copper losing electrons and then they would end up in solution because you can't have a solid chunk of copper ions, but you can actually have them surrounded by water dissolved in the solution here. So they're going to go into solution there. The silver ions are coming out of solution and they are forming a solid buildup on this cathode. The salt bridge is going to start balancing out these charges because if these copper ions keep coming off and going into solution, this solution is going to start becoming quite positive as you keep pumping in positive ions to it. And so what's going to happen is that we are going to end up with the anions moving into this solution through our salt bridge, and we're going to have the cations because this was solution over here. Remember, this was silver nitrate, right? We can't just have one ion in there. So this was copper nitrate. So we're going to have a positive cation and a negative anion. And so as we lose, as the silver ions here pick up electrons and they get deposited on there as solid metal, this solution ends up having more negative ions in it than positive ions, so it's not neutral anymore. So to balance that out, the cations are going to move through the either porous barrier or salt bridge into this solution. It's not that they're attracted to the cathode, they're just moving to the solution that has the cathode because that solution is becoming more and more negative as we lose our cations through the reduction reaction. So we can write the half reactions. It's a little bit more clear than drawing a whole bunch of ions flying around. And so silver ions are going to be picking up these electrons to form silver solid. And over here we have our copper anode metals, atoms that are losing their electrons and forming those ions. And the electrons are traveling through the wire over to the positive cathode where the silver ions are picking those up and coming out of solution and forming solid silver onto the cathode. We want to add them together to get to an overall reaction. Do note that copper is producing 2 electrons and silver is only consuming 1, so that is going to have to happen twice in order to get our balanced overall reaction. Inert electrodes are going to be like that last example. And you notice we had a silver cathode. The fact that it was made of silver didn't matter. The solid silver wasn't doing anything. We were reforming new solid silver. The silver ions were really important because they were going through that reduction. They were our strong oxidizing agent, so they were important. But the electrode itself, it was made of silver, but it could have been inert. It could have just been anything that could drop off electrons to those silver ions. So inert electrodes are essentially where we decide whether the electrode actually needs to take part in the reaction or not. And if it doesn't need to take part in the reaction, we can just use anything that conducts electricity. So essentially, an inert electrode just allows a transfer of electrons in and out of the solution, and the reaction is happening with just the stuff in the solution. So an example here, we have, again, the same anode we had before. We had copper and copper ions, and so in this case, the copper would be losing its electrons and becoming the copper ions. And over here, these dichromate ions with the hydrogen ion as well, acidified dichromate, it is going to be picking up the electrons. So these electrons are moving over here, and this solution is going to be taking those electrons and going through a reaction. We need to get the electrons to those guys in solution, and you can't just clip an alligator clip onto an aqueous solution. But what you can do is you can use an inert electrode, and you can bring those electrons over. So the copper would be losing them. You can actually connect a wire to this inert electrode for those electrons to transfer through. And then if this is in solution, this inert electrode can deposit the electrons into the solution for the reaction to take place. So in this case, the dichromate is going to be reduced. It has the hydrogen ions in there as well. And this reaction is going to happen within the solution, so we don't need the electrode itself to take part in the reaction. So we could just use any inert electrode. In this case, carbon works really well. If it's a graphite carbon, we know it can conduct electricity, and it's not going to take part in the reaction, so it's called an inert electrode. All right, cell potential for these things. On the redox table, we can see the numbers written next to the half reactions. We can put those together and figure out what is the potential difference or the voltage that this galvanic cell is going to be able to generate. So an analogy to understand cell potential is to compare it to elevation. For elevation, or altitude, we use sea level as our baseline. And when you're above sea level, you can talk about how far above sea level you are. So if you're at Mount Everest, it's like 8,000 meters above sea level. If you're at Death Valley, you're actually below sea level. And so we're using this sea level as our base for how far above or below you are, depending on where you are in the world, above or below sea level. And so it is our 0 point. We could have found the lowest part on the Earth, and we could say, okay, that's going to be our 0 point, and then above that, and we'd say, okay, this is 86 meters above the lowest point on Earth. But it's a lot easier to use a sort of standard, say, sea level, where you can do very easy comparisons to. And so that's similar to what we did with cell notation. We took a generic hydrogen half cell, and we said, okay, whatever the reaction is for this hydrogen half cell, we're going to set that to be our 0. And then we have things that are stronger oxidizing agents. So we have our stronger oxidizing agents up here. And whatever their difference is from hydrogen to where they are, we're going to assign them a potential difference. And then there are ones that are weaker oxidizing agents as well. When they go through their reduction reactions, we're going to assign them numbers that are below our 0 value of our hydrogen half cell. So sea level versus our cell potential. And again, we have chosen a particular point as 0. It would have been different if we chose the lowest half reaction to be 0. We haven't. We've chosen hydrogen half cell to be 0. And so what you'll see on your redox table is we have the half cell potentials written in as negative as long as they are below the hydrogen half cell, and as positive as long as they are above the hydrogen half cell. So the hydrogen half cell essentially is hydrogen that is assigned this 0 value, and again, it is arbitrary. We could have chosen anything to be 0 value and then had them on either side of it. And it consists of a inert platinum electrode and a 1.0 molar hydrogen ion solution. And we give it the value of 0 volts as its cell potential for that half reaction. So when we go to do a reaction, we're obviously going to have a reduction and an oxidation. And so we can find the actual cell potential of those two redox reactions. This is the equation that we can use to do that. So using those voltages, potential differences given on the redox table, we can find the potential difference, or as most people would say, voltage for the cell, by taking the voltage of the reduction at the cathode. It's important to realize that this is a reduction at the cathode, and we subtract from that the reduction at the anode. I know what you're thinking. You're saying, why would reduction be happening at an anode? And it isn't. We know that the anode is where the oxidation happens, but our redox tables write everything out as a reduction. So this is just the number for the anode taken right off the redox table. So the standard cell potential can be, the voltage can be calculated using the two half reactions and the numbers involved. And again, the reduction potential at the cathode minus the reduction potential at the anode, because that is how they're written on the redox table. If you don't like the idea of taking your reduction potential at the anode, you could say, okay, well, I know the anode is going to be oxidation, so I'm going to take that number and I'm going to flip it around. And you can do that, but just make sure you're adding it to the reduction potential of the cathode if you decide to do that. And again, all you're really doing is it's a number line, and you're finding the difference between the two numbers on the number line. So when you're adding these, the equations may sometimes need to be multiplied. So we saw with that copper and silver galvanic cell, the copper produced 2 electrons and the silver was only consuming 1, so we'd have to double the silver half reaction. Don't do that to the actual voltage. And so the reasoning for this is voltage is calculated by energy over charge. And when you double the reaction, you're doubling. So let's say you double the energy, you're also doubling the charge. And so when you do that, so for example, if it was 1 volt and you had 1 joule per 1 coulomb, that's great. If you double the reaction, you'd actually end up with 2 joules per 2 coulombs, which would give you the exact same voltage. So whatever the voltages are as given, if you double the half reaction or triple or whatever you do to it, do not change the voltage because it is accounted for in the calculation. So multiplying the equation will change the energy and the charge, and therefore the voltage does not get affected when you multiply the reaction. So a positive cell potential means that you have a spontaneous reaction. So as long as you have a strong oxidizing agent up to the left, a strong reducing agent down to the right, you will have a spontaneous reaction and you have a positive cell potential, which means you're dealing with a galvanic cell and not just a dead battery. If it is a negative cell potential, that means it is non-spontaneous. You'd actually have to put work into it, plug it into the wall to get it to go. All right, let's try this one. So we have some iodine ions and some bromine gas here. So what is the cell potential for this particular reaction? So again, we have iodine starting out with electrons, and it is becoming iodine gas because bromine here is starting out with fewer electrons and becoming, these are negative bromide ions, so they must have gained electrons. And so essentially the electrons are moving from the iodine to the bromine. So if we look at the reduction, we know that's happening at the cathode. We know the reduction is gain of electrons. We know we're dealing with a strong oxidizing agent. This is the bromine, as we saw here, gaining the electrons from the iodine. And if we look on our redox table, we can see that the reduction potential for that half reaction is 1.07 volts. At the anode, where we have the iodine, remember, anode is where oxidation happens. So oxidation is loss of reduction. So it's a strong reducing agent. Iodine is going to be losing its electrons and forming this iodine gas, and it's the same number of electrons, so we don't need to worry about it in terms of multiplying the equation. But if we look on our redox table, we see that it has a reduction potential, because the redox table is written reduction half reactions, of positive 0.54 volts. And so if we want to know what the actual cell potential is for this overall reaction, we can use our equations, and again, take the reduction potential of the cathode, the reduction potential of the anode. Realize that I have written this as an oxidation reaction. I've put a little R here so I know I have not changed, I have not flipped the actual value of the voltage. I've still written it as reduction. And so, not that we would in this case, but again, if we had to multiply one of these reactions by something, we would not multiply the voltages. Do not multiply those voltages, even if the reaction is multiplied, because it's accounted for in the values themselves. So the potential of the cell, again, take the reduction potential of the cathode minus the reduction potential of the anode, the two numbers we have there, and we end up with a 0.53 volts. If you don't like saying that, if you don't like using the reduction potential at the anode, because you know the anode is actually an oxidation reaction and you want to flip the reaction, because that's what we did when we wanted them together, we can change the sign of this and talk about the oxidation potential at the anode, which is fine, but you'd be adding the oxidation potential if you do that. And so we flipped this to be a negative because we said, all right, that anode's going to be oxidation, so I'm going to flip the voltage around as well, which is fine. But if you do that, the equation is that you're adding them together, and you get the same answer as well.